We live in this incredibly complex, high-tech world, right? And everything's designed to work flawlessly. But what happens when it doesn't? What happens when just one little part fails? And how do we even begin to understand the crazy chain reaction that could follow? Well, that's where this really powerful tool called event tree analysis comes in. And today, we're going to break down exactly how it works. So let's start with a really simple, but, a super critical question. What happens when just one thing goes wrong? I'm not talking about some massive system-wide collapse from the get-go, just a single initial failure. The real mystery is, where do we go from there? Just think about it for a sec. It could be something like a pump that just stops in a chemical plant, or a sudden power surge hitting a data center, or heck, even a simple human error, someone pushing the wrong button. These are the sparks, the first dominoes to fall. The real challenge, the whole point of this, is mapping out everything, and I mean everything, that could possibly happen next. All right, so how do we even begin to tackle that kind of uncertainty? How do you chart a path through chaos? Well, you do it by systematically charting the consequences. And luckily, there's a specific method designed for exactly that. It's called event tree analysis, or just ETA for short. And what's so cool about it is its approach. It's what we call an inductive method. Now, what does that mean? It means it starts with that one single event, our first domino, and it logically looks forward in time. It maps out every possible sequence of events that could follow, calculating the odds of both success and failure at every single step. Honestly, the absolute best way to picture this is like a choose-your-own-adventure book, but, for engineers and risk managers. The story kicks off with a problem, and at each stage, there's a safety system. It can either work, sending you down one path, or it can fail, sending you down a totally different one. Each path leads to its own unique ending, and ETA creates this amazing, complete roadmap of all those possible futures. Okay, so that's the big idea. But how do you actually build one of these roadmaps? It's not just random guessing. It's a very logical, very structured process. So let's walk through it. So it really just breaks down into 5 main steps. First, you have to define that single initiating event. Let's use an easy example. A fire starts. Step 2, you identify all the safety barriers that are supposed to kick in order. So things like the smoke detector and then the sprinkler system. From there, for each of those barriers, you draw 2 branches, one for success and one for failure. This creates all these different paths. And the 4th step is to define what the final outcome is for each path, anything from a minor, controlled incident all the way to a total catastrophe. And then the last and maybe most important step, you calculate the actual probabilities of each path, turning a simple visual map into some seriously hard data. Now, this next point is absolutely crucial, because it's where a lot of people get mixed up. ETA is all about looking forward. But what happens if you need to look backward? Well, that's where its counterpart comes into play. Just think of event tree analysis as the strategist. It starts with a potential cause, that initiating event, and it's constantly asking, okay, what if this happens? It's gaming out all the possible futures to really understand the full spectrum of consequences. Then you've got fault tree analysis, or FTA, and this is the detective. It does the complete opposite. It starts with a known failure, the catastrophe at the end, and it works backward, asking why. Why did this happen? It meticulously follows the evidence back in time to find all the possible root causes. And when you see them side by side like this, the difference just becomes crystal clear, right? You can see FTA is deductive. It works backward from a known failure to find the cause. Meanwhile, ETA is inductive. It starts with a trigger and pushes forward to find the consequences. They really are 2 sides of the exact same risk analysis coin. So, and this is the best part, you don't actually have to choose between them. When you combine the detective work of the fault tree with the strategic foresight of the event tree, you get something called the bow tie model. And it's awesome. On the left side, you've got the fault tree showing all the causes leading to an event. And on the right, you've got the event tree showing all the consequences flowing from it. It gives you this perfect 360-degree view of any potential risk. All right, so theory is one thing, but where does this analysis actually make a difference in the real world? Let's take a look at where it really shines and where it has its limits. So the key strengths of ETA really come down to clarity and numbers. It gives you this incredibly clear visual map of all the failure pathways, but it's not just a pretty picture. It puts hard numbers, actual probabilities on each outcome. This makes it an amazing tool for evaluating how well your safety systems are actually working, and for explaining really complex risks to stakeholders in a way they can just instantly get. But, no tool is perfect, right? It's really important to know the limitations here. The classic ETI model is static. It's like a snapshot in time. Its simple success or failure logic can sometimes oversimplify what's happening in reality. And by its very design, it can only look at one single starting event at a time. And maybe the biggest one, the quality of your results is only ever as good as the quality of the probability data you put into it. Garbage in, garbage out.
But when it's applied correctly, wow, the impact is just undeniable. Get this. In a study of maritime accidents, researchers found ETA was, and I'm quoting here, substantially superior to conventional statistical methods. And why was that? Because it allowed them to mathematically prove that poor visibility was the single most critical factor to fix. That's the kind of life-saving insight that other methods just couldn't deliver.
And it's not just for things like ships or nuclear plants. It's been used in food safety, too. For example, to model the risk of contamination in corn. The analysis was absolutely instrumental in pinpointing the system's weakest links, what engineers call single points of failure. Those spots where just one little breakdown could take down the entire supply chain. So this tool has this really rich history, right? From nuclear safety back in the 70s all the way to our food supply chains today. But its evolution is far, far from over. So let's take a quick peek at the future of forecasting risk. The biggest leap forward is all about making these models dynamic. The future isn't a static diagram anymore. It's something called DETA, or dynamic event tree analysis. And its superpower? It adds the dimension of time into the mix, modeling how things like human interventions and system behaviors actually change as an incident is unfolding. And this is where things get really, really exciting. Imagine pairing these dynamic models with AI to process just massive volumes of data for way better accuracy. Or what about integrating real-world big data to constantly update the probabilities in real time? We're literally moving from just analyzing risk after something bad happens to potentially managing it live with predictive models. Which kind of leaves us with this final big question. Our world is only getting more complex, more interconnected every single day. So the crucial question isn't just about the tools themselves, but about how we're going to use them. How are we going to leverage this incredible power to not just predict what might happen, but to actively build a safer future for all of us?